This is day 2 of notes. Today, the two objectives we will be going over in the notes are simplifying radicals involving I, 2, recognizing a pattern with imaginary numbers in order to solve powers of I. Okay, so before we can dive into objective number 1, which is simplifying radicals involving I, first we need to recall what we learned from the notes yesterday, which was up to this point, you have been told that you cannot take the square root of a negative number. Why is that? You can pause the video and think about that for a second. Okay, so the definition, remember, of a square root is two numbers that are the same being multiplied together to get some sort of quantity. So for example, if you had the square root, if you had the square root of 4, right? The square root of 4 is equal to 2 because 2 times 2 is equal to 4, right? 2 and 2 are the same number. When multiplied together, they give you 4. Yes? Okay, now, the reason we can't take the square root of a negative number, so if we think about the square root of negative 4, what two numbers are the same that when multiplied will give me negative 4? Hopefully you guys know there aren't two numbers, because in order for us to get a negative number, one of those numbers has to be negative, right? So I have 2 times negative 2. 2 times negative 2 is not, or they are not the same, right? If I were to put a negative in front of this negative 2, so I'd have negative 2 times negative 2. They are the same number, but do negative 2 times negative 2 give you a negative 4? They do not, right? So this is why we cannot take the square root of a negative number, okay? Therefore, this would be an imaginary number because we can't take the square root of a negative number. Now, from yesterday's notes, we learned that the square root of negative 1 is also an imaginary number. Okay, again, because there are not two numbers that when multiplied together that are the same equal negative 1. So how we represent the square root of negative 1 is with I. Okay, so no longer, guys, previously in classes, you would just say the square root of a negative number cannot be simplified or is no solution, whatever the case may be. No longer will you do that. Okay, whenever you see the square root of a negative number, you now need to identify it as an imaginary number by using an I. Okay, and we'll go through what that potentially looks like. Okay, from this point forward, you'll be able to take the square root of a negative number. I is equal to the square root of negative 1. Then I squared is equal to negative 1. So really quickly, if I were to substitute the square root of negative 1 in for I right here, you're going to be left with this, correct? And we know that square undoes a square root, therefore you're left with negative 1. So if you're following along at home, the square root of negative 1 is an imaginary number. Can somebody please tell me, what is I squared? Hopefully in your head you are thinking, this is a real number. So when dealing with imaginaries, you gain something, the ability to deal with negatives inside of square roots now, right? So if you think about that, in previous classes, you weren't allowed to simplify something that was negative underneath the radical, or you weren't allowed to, you would just say that it was a no solution. Now that is not the case. But we also lose some of the flexibility and convenient rules used when we were dealing with square roots. While using the product property of radicals allows us to show or simplify a problem, such as square root of 10 times square root of 10 equals square root of 100 equals 10, this property does not hold true when dealing with square roots of negative numbers, or another way to put that is when dealing with imaginary numbers, okay? So therefore, the square root of negative 10 times the square root of negative 10 does not equal the square root of 100. Normally, if we had the product property of radicals, we could multiply whatever's underneath the radical times whatever's underneath the radical. That is not the case with imaginary parts, okay? So before we can multiply two things underneath a radical, if they happen to be imaginary, and I would highlight this, guys, to make sure you really know this, you must pull out the imaginary part first, always, okay? You must pull out the imaginary part first, always. Now, what's cool about that is if we look here, down here, you'll be able to see if I pull out the imaginary part in both of these, I have I square root of 10 and I square root of 10. Now, some of you might, like, how did they go from square root of negative 10 to I square root of 10? Well, that's what I'm here for. So, square root of negative 10, okay? Based on our product property, we can pull radicals apart. So, hopefully you guys all agree with me that the square root of negative 10 is the same thing as the square root of negative 1 times the square root of 10, right? Because if I were to multiply these two together, I would be left with the square root of negative 10. Okay, well, I can pull them apart, and based on what we talked about earlier, I know the square root of negative 1 is I, right? So I'm going to represent that with my variable I, and then I square root 10. So that's how they got I square root 10, I square root 10. Now, what's cool about this now is the radicand, or the number underneath the radical, is positive. So now we can go back and use our product property of radicals. So since the radicand is now positive, I can multiply those two things underneath my radical. So 10 times 10 is indeed 100. And then just like you would multiply radicals together, you multiply their coefficients, or the outside numbers. So I times I is equal to I squared. Make sense? And based on what we talked about earlier, we know I squared is negative 1. So you have negative 1 times 10 is equal to negative 10. Okay? Now we're going to go over more examples, but what you need to make sure you take out of this particular section of the notes is that before you do anything, it doesn't matter, simplify, multiply, divide, whatever it is, you must take I out first before you do anything else. Okay, that's where most of the mistakes when dealing with imaginary numbers lie. All right, let's do some examples. Okay, so this says simplify each expression. So in number 1, we have the square root of negative 24. Hopefully by now, based on what we've talked about over the last day and a half, you've recognized that this is an imaginary number because there is a negative underneath the radical. Okay? Remember what we talked about just a second ago, that in order to simplify, in order to do anything with a radical, the number underneath, or the radicand, must be positive. Okay? So currently we cannot do anything. But if we remember, we can break this apart based on our product property. So this could be the square root of negative 1 times the square root of 24. Notice, I have not changed the problem at all, right? All I've done is simply write the square root of negative 24 in a different way. Now, once we get to here, I know the square root of negative 1 is I. So I'm going to put I to signify that it is indeed an imaginary number. Okay? And then I have the square root of 24 left. Okay, now what's cool about this, guys, and hopefully you figured this out, is once I pull the I out, if I look at this part right here, this is literally the review standard. This is why it's so important that you really take the time to make sure you understand all of the stuff that you did in algebra and intermediate algebra, because it's going to make advanced algebra so much easier. So once I pull out the I part, right, which is the advanced algebra stuff, now it turns into intermediate algebra, which hopefully is very, very easy for you now. So what I'm going to do is factor tree. So the square root of 24 is 2 times 2 times 2 times 3. We know the index is 2, so I'm looking for groups of 2. There's my group of 2. I'm going to pull one out. So I'm left with 2 square root 6. Now, that is the real part, correct? This is where the advanced algebra part comes in, okay? So you've done your intermediate part. The last thing you have to do, we know that this thing is an imaginary number, and that's outside the radical, right? So I'm going to make sure I have that I to signify that the thing that we dealt with was imaginary. So your answer in simplified form would be 2I square root 6. Next, we have the square root of negative 81. So again, the first thing you have to do before you do anything else is pull out the I, right? So what I'm going to do is do that. Again, product property, you have square root of negative 1 times the square root of 81, okay? I now know that the square root of negative 1 is I. So this is I times the square root of 81. right? Now my radicand, or the number underneath the radical, is positive. Therefore, I can use my rules and do what I've done. Hopefully, everybody in this room has realized the square root of 81 is indeed 9. So my answer would be 9i. Okay, and the reason it's 9i is because did this start out as a negative underneath the radical? So we have to tell the world that it is imaginary. Okay, what I would do if I were you is pause this video, see if you can do number 3. I will have the answer and the explanation in just a sec. All right, number 3. So what we're going to do again, we have an imaginary number. We know it's an imaginary number because there is a negative underneath the radical. So the first thing we're going to do is pull out the I part. Again, that's what you have to do every single time. So you have the square root of -1 times the square root of 121x to the 5th. This is perfect because now we've made the number underneath the radical positive. So I have I square root 121x to the 5th, which is great. Now underneath the radical is positive, so I can do exactly what I did in intermediate algebra. Based on our factor tree, I know that 121 is indeed a perfect square. 121 is 11 times 11. I will rewrite that as the square root of 11 times 11 times x to the 5th. Since I know the index is 2, I'm looking for groups of 2. I pull 111 out. So now I'm left with 11i square root x to the 5th. Again, you can prime factor this out as x times x times x times x times x if you would like. I am not going to do that because I feel like it's a little bit easier to think of it as if the index is 2. I have 2 groups of 2x's. And I have 1 left over. So my final answer would be 11i x squared square root x. Again, I would encourage you to pause the video, and then we will get back to number 4 in just a second. Okay, number 4, again, negative under the radical. We must pull out the I part first. So I have the square root of -1 times the square root of 200x. I change the square root of -1 to I, like we've talked about previously, times 200x. Now what's great about this, guys, is again, underneath the radical is positive, which is what we want. Because if the underneath the radical is positive, is it just intermediate algebra? So again, I can't stress to you enough how important it is to really know those radicals, okay? All of the properties of radicals. If you do, this is definitely within the realm of you being very, very successful. Okay, so you have I square root 200. I'm going to prime factor this guy. So we have 20 and 10. And then I have 4 and 5, 2 and 2, and 2 and 5. Okay, so on the outside, I'm left with I square root 2 times 2 times 2 times 5 times 5. Okay? Again, the index is 2, so I am looking for groups of 2. So I have a pair of 2s, and I have a pair of 5s. I bring 1 out, bring 1 out. You're left with 2 times 5 times I, and I have a 2 left over inside and an x. Okay, I just multiply the outside, so I'm left with 10i square root 2x. Hopefully we are starting to get more and more correct, and we will move on to number 5. Now that's something we haven't seen before, but I would encourage you to use what you know about polynomials and see if you can come up with the correct answer. All right, so before we do anything, I want to rewrite this as 8x times 3x, just really quickly, to prove to you that I, even though it's representing a number, an imaginary number, it still is just a variable, right? I think everybody in here knows how to do 8x times 3x. If we were to multiply those two things together, 8 times 3 is 24, x times x is x squared. Okay, so we're literally going to do the exact same thing here, only we're going to have I. So 8i times 3i is equal to 24. Again, you multiply the coefficients, and then you multiply the variables. I times I is I squared. Now, what makes it just a little bit more challenging, or the fact that you have to go just one more step, is that we know that I squared is a real number. And I squared, if you recall from page number 1, is equal to -1. So since I know this is a real number, I'm going to substitute -1 in for I squared. So you're left with 24 times -1, because I squared is equal to -1. 24 times -1 is indeed -24. Moving on to number 6. Okay, so number 6 is us multiplying two radicals together. Now normally, like we had talked about before, when you multiply two radicals together, you would multiply the inside with the inside. That's if they were positive. But since they are imaginary, again, the reason they're imaginary is because you have a negative sign underneath the radical. Okay, so if you have a negative sign underneath the radical, you know it's imaginary. If you know it's imaginary, before you can use any property, do anything at all, you must pull out the I first. Again, so how we would do that is the square root of -1 times the square root of 5. Again, that's the product property of radicals. Square root of -1, square root of -1 times the square root of 20. So I'm now left with I square root 5 times I square root 20. So there's a couple of different ways you can do this, right? Some of us might find it beneficial to multiply the outsides and multiply the insides. Others might find it beneficial to simplify both radicals and then multiply it. For me, I would like to simplify both radicals before I multiply it because I'm dealing with smaller numbers, and I know I probably won't make a mathematical error if I'm dealing with smaller numbers. So if I looked at this one, we know that this cannot be simplified, but I square root 20 can. So if I were to simplify that, this would be the square root of 20, so that's 2 times 10, and then 2 times 5. So therefore I have a group of 2, so those 2's come out. So I'm left with then I square root 5 times, I have 1, 2 outside, so that's 2I, and I have a 5 left in, so that's square root 5. Okay, now, these are both simplified, so now all I'm going to do is multiply the outsides and then multiply the inside. So if I were to multiply the outsides, I times 2I happens to be 2I squared, right? I times I is I squared. The insides would be the square root of 25. Yes, 5 times 5 is 25. Okay? Now, from here, we still have to go on, don't we? Because the square root of 25 potentially could be simplified. Hopefully a bunch of us recognize that the square root of 25 is indeed a perfect square. Square root of 25 is 5. So I'm left with 2I squared times 5 now, right? Because the square root of 25 is 5. 2 times 5 is 10, so I'm left with 10I squared. Now, in previous classes, like if this was just a variable like x, you would be done, right? But light bulbs have to be going off in your head if you see I squared, okay? I squared, we had just talked about, it is a real number. Therefore, you should represent that, right? Okay, so I squared, we said, is -1. So let's plug -1 back in for I squared. So that is 10 times -1. Therefore, my answer would be -10. All right, moving on to our second objective, which is recognizing a pattern when dealing with powers of I and being able to simplify it, okay? So if we look at this table, we have n, which is the exponent we're going to raise I to. So for example, this one would be I to the first, and we know I to the first we've talked about is I, okay? That obviously makes sense. We also know, since n is 2, that's I squared, right? And I squared, we know, is equal to -1, like we have talked about already, okay? Now, let's move on to I to the third, we know is -I, okay? And I'm going to prove that to you right now. Do you guys agree that if I had I to the third, I could break that up into I times I times I, yes? I hope you do, because that is correct. All right, now what I'm going to do then, so I to the third is the same thing as I times I times I, okay? And now that I have 3 i's being multiplied, I can break that up any way I want to. So what I'm going to do is take I times I and make that I squared times I. So all I've done, guys, is take I to the third and rewritten it a different way. These two things are equal, yes? And the reason I wrote them as this is because I know, based on what's already in my table, what I squared is and what I are, correct? So I know I squared is -1. I know I is just I. Therefore, I to the third is -I. Does that make sense to everybody? Okay? Because as we get farther and farther along and we get higher and higher exponent, it's going to be vital that you know how to rewrite the exponents in a way that's going to be beneficial for you. Okay? All right. So let's go to I to the fourth. Okay? If we went to I to the fourth, let's rewrite that. So if I have I to the fourth, I to the fourth, we're going to rewrite that as I times I times I times I, right? We all agree that that is indeed I to the fourth. Well, there's all kinds of different ways that we could break this up and rewrite this, right? I could, if I wanted to, say this is I to the third times I, yes? Because I to the third times I is indeed I to the fourth. So we've rewritten it in one way. I could also say this, couldn't I? That I could break this up into I squared times I squared, correct? Again, I squared times I squared is indeed I to the fourth. So now there's 2 different ways that we potentially could rewrite this. Again, it's whatever best suits you. Does that make sense to everybody? Okay, so all I'm doing here is just proving that I to the fourth is indeed 1. I like the blue one because I know I squared is a real number of -1. I know I squared is a real number of -1. And I also know -1 times -1 is 1. So do we match the table? Okay, what's not filled in though is 5, 6, 7, and 8. Okay, so I'm just going to go over I to the fifth real quick. Okay, and then I'm going to ask you guys to see if you can come up with the answers to I6, I to the 6th, I to the 7th, and I to the 8th. So I to the 5th, I can break up into, or as, I times I times I times I times I, right? And now I can break it up into all sorts of different ways, okay? My personal opinion is I want to break this up into I to the fourth times I. And the reason why I want to do that, hopefully we have somebody, no, I just thought I was teaching a class, ha ha ha. Right? There's nobody that's going to answer me. So I'm going to rewrite this as I to the fourth times I. Again, I to the fourth times I is I to the fifth. So all we've done, guys, is rewritten I to the fifth a different way. And hopefully you can see why I would want to write this as I to the fourth times I. Because I to the fourth, we know, based on our table, is 1, right? So 1 times I is just I. Y'all agree? Okay, now, if you want to, I would strongly suggest you pause this video and I would try to break up I to the 6th, I to the 7th, and I to the 8th in I to the 4th and see what you get for an answer. All right, I to the 6th. Again, I'm going to rewrite it. If you can already see how to break it up, by all means, go for it. Okay, so that's 6 different I's, right? What I'm going to do is break this up into 4 I's. Again, and the reason why I want I to the fourth is because I to the fourth is equivalent to 1, correct? So I have 4 i's. I can rewrite this as I to the fourth times, I have 2 i's left over, so that's I squared. So you guys can see I to the fourth times I squared is indeed I to the 6th. Therefore, I have not changed the problem. I to the fourth is 1 times I squared, which is -1. So I to the 6th is equal to -1. Hopefully you're starting to see a little bit of a pattern here. I to the 7th, I can break up into I to the 4th times I to the 3rd. I to the 4th is 1. I know that I to the 3rd based on the table is -I, therefore I to the 7th is -I. I to the 8th, I can break up into I to the 4th times I to the 4th. So that's 1 times 1. So I to the 8th is 1. Now, hopefully you guys have seen a pattern, right? It starts over at I to the 5th, okay? I do not want you to think about it starting over, though. What I do want you to think about is the reason it's starting over is because of this I to the 4th that I can find in each one of these. And would you agree, it doesn't matter how many I to the fourths I find since they're all 1, and 1 times anything is just 1. That is going to be vitally important as we move on to the following examples. All right, let's look at number 1. So it's I to the 15th, okay? If you haven't picked up the pattern yet or picked up what I'm trying to put down here, it's that we're trying to find as many I to the fourths as humanly possible. Because we know that I to the fourth is equal to 1. We also know that 1 times anything is itself. So this first one, bear with me. I'm going to write everything out and show you what we're doing, and then hopefully we'll come up with a more efficient way down the road as far as the examples go. Okay, so I to the fourth, I'm going to rewrite, I to the 15th, I'm going to rewrite all of the i's. So I need 15 different i's. Okay, so I have 15 different i's. Again, I to the 15th and all of these multiplied out are the exact same thing. We just rewrote it a different way. And you guys are going to find out the farther we get on in this particular class, the more essential it is to be able to write things in different ways, because you might not be able to solve it the current way it's written, but if I rewrite it a different way, it becomes very, very easy. Okay, so we said that the goal of this is to break this up into groups of 4, right? Well, I have one group of 4 i's. I have 2 groups of 4 i's. I have 3 groups of 4 i's. And then I have 3 left over. And again, hopefully you're answering these questions in your head as you're listening to this. The reason why I want to look for groups of 4, so this is I to the 4th times I to the 4th times I to the 4th times I to the 3rd, is because I to the 4th is equal to 1. And we know that 1 times anything is itself, right? So 1 times 1 times 1 times I to the 3rd, these guys essentially don't matter, correct? So all I'm left with is I to the 3rd. And what do I know I to the 3rd is? Negative I. Okay, now before we move on to negative 2, what am I talking about? It's early, right? It's early in the year. Before we move on to negative, I just did it again. What am I doing? Before we move on to 2, I would like you to think about this question. What operation allows me to break things up into groups? Because that's essentially what I'm doing right now, right? I'm taking all 15 i's and I'm breaking them up into groups of 4. So can you please think about what operation allows you to break things up into groups? Answer that, and then we will move on. Hopefully all you guys were like, oh yeah, I know what operation breaks things into groups. That's division, okay? So if you look at examples 2 and example 3, you'll notice that the exponent is substantially higher than 15 or any exponent that we've dealt with before. And there is no way in the world, if we had I to the 353rd power, that we would want to write out each one of our i's. So we have operations that essentially make it way more efficient for us. Okay, so we said that division breaks things into groups. So I want to, after already explaining this thoroughly by writing it out, I now want to do it maybe just a little bit different way. Okay, so we said that division breaks things into groups. So I'm going to divide 15 by 4. Okay, and the reason why I want to divide 15 by 4 is because I want to find out how many groups of 4 i's I have in 15, right? Because division breaks things into groups. So let's divide. So how many times does 4 go into 15? That happens to be 3 times. And if you notice, guys, up here, I have 1 group, 2 groups, 3 groups, right? So this 3 always, whenever you're dividing, is number of groups of 4 i's, okay? And tomorrow, I'm going to ask you a question about not only is it the number of 4 i's, but it's also something else. And I might even give you the answer in just a sec. So 4 times 3 is 12, right? And then 15 minus 12 is 3. So you notice that this 3 happens to be the 3 that are left over, or what we call the remainder, right? So this 3 is the number of groups of 4 i's. This 3 is the remainder of i's left, correct? Or this guy right here. Yes? So hopefully we're starting to understand what's going on, right? So if I have 3 groups of 4 i's, that means I have 3 different ones, yes? Just like we did up in the front or up at the top here. I have 1 group of 4 i's. 2, so this is 1. This is the first group. This is the second group. And this is the third group. And since they're all I to the 4th, do they all equal 1? Right? And then I had 3 left over. 3 is my remainder. So this is 1 times 1 times 1 times I to the 3rd. And based on the chart above, I know I to the 3rd is negative I. Does that make sense? So the farther you get up and the numbers get farther away from 0, they get bigger, guys, we want to use division. So we don't have to write out every single I and put a box around the groups of 4 i's. Does that make sense? Okay? All right, so let's do number 2. Number 2, again, we're looking for groups of 4 i's because 4 i's, I to the 4th is equal to 1, and 1 times anything is just itself. So in order to break things into groups, we're going to divide. So 99 divided by 4. So 4 goes into 9 2 times. 2 times 4 is 8. That's 1. Bring down the 9, right? Okay. 4 goes into 19 how many times? That's 4 times. Okay, so 4 times 4 is 16. I'm left with 3 left over. Here's a $1 million question. How many groups of 4 i's do I have? Hopefully everybody in here said I have 24 groups of 4 i's. Okay? Another way to say that is I literally have 24 ones being multiplied together, correct? Because I have 24 groups of I to the 4th. And this is 24 times, yes? Okay, hopefully that makes sense, right? And then, based on my remainder, I have 3 left over, don't I? So that means I have 3 i's left over, so that's I to the 3rd. And what do we know I to the 3rd is equivalent to? Negative I. So this would be 24 times I to the 3rd, and I know I to the 3rd is equal to negative I. So my answer would be negative I. So I to the 99th power is negative I. See if you can do number 3 by yourself, and then click the play button. All right, here we go. Again, you are dividing by 4, so let's divide 154 by 4. Or 158, sorry. 4 goes into 15 3 times. So 3 times 4 is 12. I bring that down. I have a 3. I bring the 8 down. So how many times does 4 go into 38? That happens to be 9 times. So 9 times 4 is 36. I have 2 left over. Again, this 39 is the number of what? I to the 4ths, or the number of ones I'm multiplying, correct? So I have 39 different I to the 4th being multiplied together, right? And we know that I to the 4th is equal to 1, so it's really just 1 times 1 times 1 times 1 all the way until I get to the remainder, which would be I squared. Do you guys agree with me on that? Hopefully you do. Okay, and what do I know I squared is based on that table and based on what we just discussed? I know that is negative 1. So I know that I to the 158th power simplifies to negative 1, or is indeed a real number.